The Retort Season 1 presents expert views on the BTWC and CWC and the issues they face. This project is the product of a collaboration between Professor Li-Jun Shang, Professor Malcolm Dando and Dr. Brett Edwards. This initiative has been funded by the London Metropolitan University Rescaling Fund 2021, which was awarded to Professor Li-Jun Shang. We are grateful for this support.
Hello and welcome to this series of talks on the subject of chemical, biological weapon disarmament and non-proliferation. In this series, we will be hearing from a wide range of experts as we look towards the two major review conferences which will be taking place in coming months. In each talk, you will hear from a respected expert who will outline key opportunities and challenges in making pragmatic and holistic progress on this issue globally. This project has been kindly supported by the London Metropolitan University.
Ladies and gentlemen, it gives me great pleasure to give this talk to you today. My name is Ralf Trapp. By training, I'm a chemist, and I've worked in the field of chemical toxicology for most of my professional life. Many of these years I've spent working on issues to do with arms control related to chemical and biological weapons. I did participate as a technical expert in the negotiations of the Chemical Weapons Convention and was there during the final phase of the negotiations of that treaty. Thereafter, I worked 13 years at the OPCW in various functions, and since 2006, I am an independent consultant on chemical and biological weapons arms control and provide consulting services to several international organizations, including the United Nations, and in this context, UNODA and the Implementation Support Unit of the BWC, also the OPCW, as well as the European Commission, several national governments, and a number of research institutions. My presentation today will deal with developments in the chemical, life, and associated sciences. This is meant as an introduction to other presentations, which will go into much more depth about some of these issues that I can do in this short presentation. So I will be posing rather more general questions. What does science and technology have to do with the norms against chemical and biological weapons? What can scientists and engineers do to support the regime that prohibits these weapons? And what is it that governments may wish to consider when they prepare for the upcoming review conferences of both treaties? How can they reap benefits emanating from the advances in science and technology, whilst at the same time guarding against the possibility of misuse for malevolent purposes? Before I go into the developments in science and technology, let me simply state again, recall that chemical and biological weapons and warfare as we know them today would not exist without science and technology. Just to use chemical weapons as an example, scientific knowledge about chemistry and chemical materials, as well as experimentation in laboratories, enabled the synthesis and characterization of poisons that were selected as chemical warfare agents. The chemical industry at the early 20th century provided the technologies and the equipment necessary to manufacture these agents at industrial scale. And technical and engineering innovation, such as gas compression, aerosolization, and others, made it possible to use these selected agents effectively on the battlefield. On the other hand, science and technology, scientific methods, and instrumentation have provided the tools to protect us against the effects of chemical and biological weapons. They have given us protective clothing, respirators, medical treatments, means of decontamination, and more. And science and technology have also been called upon when it came to negotiating and perhaps even more so implementing the Chemical Weapons Convention as well as the Biological Weapons Convention. We needed scientific understanding and technology to safely and efficiently eliminate the weapons concerned. In the case of the Chemical Weapons Convention, we needed technology and science to devise methods of verification and investigation of suspected treaty violations. And in the context of the Biological Weapons Convention, of course, we have provided scientific advice to governments in for developing preventive strategies to manage the advances in science and technology. Arms controllers need to be able to evaluate what impact the advances in science and technology have on their treaties. They also need to understand what impact the treaties would have on entirely legitimate activities involving relevant materials, equipment, and technologies employed for peaceful purposes. Some of the questions that scientists need to ask themselves when they have these conversations have to do with the fundamentals of the regimes. They relate to scenarios where scientific discoveries or new emerging technologies may challenge the very scope of the prohibitions of those treaties. The kinds of questions to be addressed are these developments, these new materials and technologies, actually covered under the treaties? Do the treaties protect us against any possible misuse? Other questions relate to the way in which treaties function, and the way in which they are being implemented. They reflect changes in the implementation environment that may call for adaptation of the way things are done in practice. Are national implementation measures still adequate? Or should state parties adapt regulations different from what they're doing today, or other forms of administration? Do international mechanisms, such as verification or international exchanges, international cooperation for peaceful purposes, require intention and perhaps adaptation in the way we are managing these? Let me give you first a couple of examples of the first kind. What you see here is a compilation of images and references to scientific publications to do with DNA nanostructures. And as you can see from the slide, these are all not just nanoparticles as we have seen them in discussions in the context of the Biological Weapons Convention, but also in the Chemical Weapons Convention context as delivery systems. But these are more complicated systems and structures. Some of them are mobile devices that could move things around. Others are container type nanostructures that could be used as a delivery vehicle for example, poisonous substances, or also for DNA, for RNA, for proteins, for other types of biomolecules that may be of interest in the context of biological warfare. Now, when we're looking at these pictures, and they look, I admit, a little bit futuristic, at least some of them still do, then we're asking ourselves, what are these things? Are they chemicals? Yes, they are made of chemicals. Many of these things are made of DNA. They are sort of folded into structures, almost like an origami, and that's why they are called DNA origami. And these structures can then be made to perform functions once administered into biological systems, into the bloodstream of a human being, for example. Yes, so what are they? Are they actual agents? I think not, but some of them may have functions very similar to a biological molecule. They may cut long biomolecules, they may cut DNA or RNA, they may interfere with the function of proteins because they seem to fit properly into certain structural elements. So are these things that we need to think about in terms of regulating them in the context of either the Chemical Weapons Convention or the Biological Weapons Convention? The possibilities of chemical structures, then, as you will see in a moment, the possibilities are vast. Many of the small molecules that exist have already been made, but if you think about the possibility of the different combinations between DNA, between the different constituents of DNA, different base pairs, both natural bases as well as possibly other bases that could be introduced, then you very quickly end up in an exponentially increasing number of options of what this molecule could look like. You can do the same experiment with proteins. You can make the same Gedanken experiment with all kinds of other materials. The numbers are vast. And this vast space of possibilities in chemistry provides an almost infinite number of new molecules and also of new biological systems or biological effects. By the way, I should have said this. This is taken from a presentation by David Winkler at the Schwyz Convergence meeting in 2018 in Switzerland. As he points out, these are spaces which, like in the cosmos, like in interstellar space around us, may be largely empty. So the trick really is to find those areas, those parts of the space where we find use for chemicals that have new properties or that have enhanced properties and then can do a number of things for us that we cannot do with our present chemistry as evolving. And how do we get into this capability? And one thing you will see pop up again and again in these discussions today is reference to machine learning and artificial intelligence. Now, this gives us a tool, it gives us a methodology and approach to really open up a completely new world of how you find new chemicals, how you optimize these chemicals. You can do this in the development of drugs, you can use it for the development of understanding with respect to toxicity. You can also combine it, and that is the other thing I wanted to point out, with other developments. For example, the development of the introduction of robotics and of automation in chemical synthesis. So if you put these things together, the ability to construct theoretically structures, chemical structures, and predict what their physiological, chemical, and physical properties are likely to be, a possibility then to synthesize such molecules in large numbers, create big libraries of molecules that fit into this category that you've just designed of chemicals, and then test them, do large screen testing and optimization. You end up with what some people have called artificial chemists, systems that include artificial intelligence, automation, and automated large-scale screening and testing to reduce the time it takes to come up with new lead molecules. And basically, they don't replace living beings like myself. They don't replace a chemist in the laboratory, but they make it much easier and much faster to find new molecules of interest. And here on the right-hand side, you'll see a couple of examples of how these spaces can evolve. Today, we have about 10 to the 4 small molecules that are actually in use as drugs in medicine. But the potential number of compounds that are available is much, much bigger. Here's a reference to the Merck assembly inventory. So this is basically a massive collection of structures that have been developed and to some extent tested, some discarded, some not further developed, some are drugs today. And we're jumping from 1 to the 4 to 1 to the 20. If you look at the stars in the universe, and they all have their own chemistry, if you think about it, we're even larger. We are 10 to the 24. And then if you look at small molecules in the chemical space that we know or that we can see today and envision today, that is even vaster. That is possibly 10 to the 63 or higher. So what you see is this combination of artificial intelligence, chemical knowledge, big data information, automation in synthesis, and automation and large-scale arrays in screening of properties. That gives us a possibility of really moving forward much faster. What does that actually mean from a chemical weapons point of view? And here's an example. It's a fairly recent example, 2021, where a group of scientists developed a generative software, a type of a machine learning tool that would generate models of chemical structures based on knowledge from existing structures about their lethality in rats, their acetylcholinesterase inhibition, which is one of the target effects of nerve agents, and then basically came up with new structures, or structures that were not in the data sets they started with at the beginning. And they did find VX. So VX was generated by that model as one of the possible structures, but they also found a whole range of other structures, some 5,000 or so compounds, theoretical compounds, which were known VX analogs or other types of agents that would have similar properties to one of the most deadly nerve agents that we know. So here's a tool that if you transport that into what would a chemical weapons program look today, what would people do today to develop new agents, then you can understand that what took years and years in the past to do would basically end up being done something within days or possibly weeks Now, this is all still on the computer. This is in silico. But with all the other developments we've seen in synthesis and in screening, it is very possible that something like that could be rolled into a chemical weapons program and new agents could be developed very, very quickly. Now, this doesn't have to necessarily lead to new toxic chemicals in the sense of lethality. It can also lead to new agents that have other effects, effects on the brain, effects on our behavior, on our mood, on our understanding of things, our perceptions. So here clearly is an issue that needs to be followed. So what do we do about this? What does that mean for the evolving risk assessment that our conventions need to deal with? Should we, in the Chemical Weapons Convention case, expand the schedules as a basis for a broader routine verification coverage? But we need to think about whether that actually makes sense. We need to create this or maintain a balance between the gains in security on the one side, but also the economic impact on the other. And finally, also the practicality of, can we actually, if we add lots and lots and lots of these new chemicals, can we actually verify these things properly? So this is not an easy answer, but it needs to be addressed, an easy question to answer, but it needs to be addressed. Do we need to rethink the whole concept, the whole structure of the relationship between the schedules and the Chemical Weapons Convention and the regime that deals with non-scheduled chemicals, the OCPF regime? Where is the gain for compliance assurance, where we put the emphasis, and what is it we need to deal with these things in the future? Also, can we think about combining the existing routine verification mechanisms in the Chemical Weapons Convention with other mechanisms, with other tools? I'm not suggesting we should change the verification system, but I'm looking at it in terms of, are there other sources of information that are equally important, if not increasingly more important, to assess whether things are going wrong somewhere? And how can we make use of those? The SAB in one of its reports mentioned a more holistic approach to verification in the chemical industry. And I think that is something to consider more carefully. Where can we actually get more insight into whether the actual risk areas are? They're not necessarily just driven by chemistry and technology. They're also driven, of course, by the strengths of other regulatory systems, by the way the industry itself regulates its conduct. After all, the chemical industry is one of the most highly regulated industries worldwide. So 25 years after the entry into force of the Chemical Weapons Convention, it is perhaps time to do what the convention presumed we would be doing at the first review conference, which is to undertake a broad review of the industry verification system in its complexity after several years of practical experience. We have reviewed many aspects of the system. There have been a few changes to the schedules. There have been discussions about selection criteria and algorithms to be used for selecting industry facilities for inspection and so on. So I'm not suggesting nothing has happened, but what I think has not been done really is a broad-based review of how has the whole industry landscape changed. What does that mean for the potential that is there in the context of the Chemical Weapons Convention, and is the approach that we've taken in the verification system still appropriate? Or do we need to do additional things? I'm not suggesting getting rid of what works well. I'm suggesting thinking about, is it what we need, and are there other things that maybe are needed as well in the future? Let me move on to some issues to do with biological weapons arms control. And one of the issues that's been hotly discussed in recent years is the question of compliance assurance and the resolution of concerns regarding non-compliance. Of course, the Biological Weapons Convention doesn't have a verification system comparable to the Chemical Weapons Convention, and neither can it rely on an implementing agency such as the OPCW. However, it seems that compliance measures in the BWC context are now finally receiving a broader political attention, support, and hopefully something practical will come out of this. One aspect of compliance assurance is, of course, how you deal with allegations of the use of biological weapons. And although the BWC doesn't have its own mechanism in this regard, There is, of course, a mechanism in place today, the UN Secretary General's mechanism. It has been used for chemical weapons issues in the context of Syria in 2013, and since then has received additional attention in order to strengthen its operational and its scientific and technical capabilities and bases. This is particularly pressing in the biological weapons case because, as I just said, the BWC itself does not have a verification protocol or a verification machinery in place, and there is nothing equivalent to the OPCW to conduct these inspections other than what has happened in the context of the UNSG. I'm going to say a few words in a moment about one aspect of this, and this has to do with the work of laboratories and the support that they can do, can render to such investigations. But it's important to remember that the challenges which the UNSGM had to confront in developing structures and developing capabilities in this field are exactly the same as the BWC will have to face once it starts looking into its own compliance assurance mechanisms. And frankly, it cannot just borrow a lot from the UNSGM and can probably become a mechanism or one single tool that the international community can use for such situations. So let me share again a couple of. This first slide dealing with issues to do with the conduct of an investigation of a possible biological weapons use was taken from a meeting report from 2015 organized by the Swedish Defense Research Institution, FOE, in Stockholm. What you see here are the different stages in such a forensic investigation, and also it illustrates the challenges that we are facing. The fundamental question for any such investigation is to distinguish between natural outbreaks of a disease and a deliberate outbreak, or also, of course, an accidental outbreak of an agent. So all this begins, of course, with the identification of the causative agent, and that's very much part of the public health response normally. We want to know what kind of an agent was it? Was it a bacterium, a virus, a fungus, etc.? We want to know more specifically what genus and species was involved, and also what the properties of the agent were. Hence, what do we need to do to prevent its further propagation and also to treat the victims that we already have. However, we do not, as yet, get a clear idea of whether or not this was a natural outbreak or whether it was a deliberate agent release. There is a background of biological agents in nature, and so we need more information to be able to actually draw that conclusion. So here comes the next step, characterization of the agent. We're going deeper into trying to understand specifically what is the makeup of this agent that we have identified. Do we have signs of genetic manipulation, for example? Do we see any mutational bias that indicates that the agent had been developed, had been nurtured in a laboratory environment? And many of the other things that we need to look at that make the outbreak unusual. So we are going for a deeper characterization. We're also looking at data that are not really lab data, things that come from epidemiology and from symptomatology. We're looking at what kinds of symptoms are there, how did the outbreak occur, what was its timely distribution, and what was the distribution in terms of space. All this gives us a clue as to whether or not this might be a deliberate outbreak. But again, we're still at a level where we cannot be certain what has really happened. Many laboratories can cover these first stages of identification and characterization to a fair degree. Laboratories from the public health sector and elsewhere. But as we move into higher complexities and want to know more about the actual outbreak, it gets more complicated, and there are fewer laboratories who can actually cover the whole spectrum. So finally, when it comes to looking at the origin, the source of such an outbreak, we really need to dig deep and get a really clear understanding of whether or not we can link the detailed information of that strain to something we know from elsewhere, from a stockpile, from previous outbreaks, whether we can link it to perpetrators, and whether we can bring other types of information, forensic data, into the assessment. So all of this is getting fairly complicated and complex, but it's necessary to go through this process and to make this discrimination between a natural outbreak and an unnatural outbreak. Hence, efforts that have been made by many laboratories over the past 10 or so years to develop concepts to get a clear idea of what are the requirements, the criteria for such investigations. Here you see just a couple, just a short selection of reports from such meetings. Already mentioned the meeting in Stockholm on the left-hand side. The reference down here on the right-hand side to Spitz Laboratory and the UNSGM Designated Laboratories Workshop report. This is from 2021. I should stress that this was the 6th report in a series. So here is a concerted and ongoing effort to move forward with identifying these requirements, but also organizing an exchange between the different laboratories and encouraging practical activities. And as we will see in a moment, things like exercises, like proficiency tests, or rather I should say, interlaboratory comparison tests and confidence building exercises to get a clearer grip on what needs to be done in this field. I also have included here a picture of Eurobiotox. This is a European initiative in the area of toxin analysis, but it goes beyond Europe. There are in total 63 laboratories involved in this project from 23 countries, and 4 of them are not EU countries. So here's again an attempt to develop capabilities in a domain that is often slightly sidelined. It doesn't quite fit into what we're doing in the context of chemical weapons analysis. Only a few toxins have been looked at in this context. And in the area of biology, the focus is very often on microbia, on viruses and bacteria. Toxins have a slightly different set of requirements and properties. And so they often sort of the fifth wheel on the car, so to say. But here's an example for what can be done in this field and what has been achieved already. So what are all these different activities bringing forward? They have taught us that it is very important to develop a whole set of understandings and criteria for such investigations. We know that we cannot rely on one single technique in the analysis. We need to use a set of complementary methods and techniques in the laboratory to be sure we get all the information we need for this kind of characterization and finally attribution. We also need to think about the methods that need to be accredited and validated. We need to be able to have, or we need to convey the trust in the methods that have been used. For that, we also need curated databases and well-prepared and validated reference standards, things that don't necessarily exist in the public sector or that don't necessarily exist on the open market. So things that need to be developed specifically for this context. And this is, of course, time-consuming, it is resource-intensive, and not an easy thing to do. And finally, we need to think about things that are going beyond classical microbial forensics and take us into other areas of forensics. The other thing that we need to look at is it's not just about the science. The laboratories concerned here need to also understand 2 other aspects. One is the procedural context of such an investigation, the ability to comply with requirements such as chain of custody, preservation, and the whole context in which such an investigation is embedded in a broader political process. And that leads us to the 3rd aspect that is important here, which is the communication side. It is how do you report the results of such an investigation to a political, legal audience that then needs to address the issue in the context of compliance assessments. What I'm trying to convey to you here is that there are complexities that need to be discussed, they need to be analyzed, but also they need to be practiced and exercised. And one of the important aspects here is that all this has in fact moved into practical exercises, into laboratories actually working together to try and develop a shared network of competencies, of understandings, of common approaches, and also, of course, sharing experiences, resources, and so on. Here is an example from a German project, Project Bio, which was initially scheduled for 2017 to 21. It has now been extended. This is a program of external quality assurance exercises which involve both bacteria and viruses, but also toxins. So we're operating at 3 different levels, and it includes both the conduct of workshops and the conduct of these quality assurance exercises between laboratories to test their capabilities, to learn from each other, to better understand the requirements and find gaps in the capabilities that the laboratories have, and to get a clear understanding of what is necessary to have an effective investigation mechanism for the future. We also need to look at it in terms of a broad participation, and you see from the map here that there has been quite some progress in terms of bringing a whole range of different countries into the spectrum, but there are also still regions which are not as well represented. So this is the technical basis on which we can then start looking at what needs to be done in the context of the BWC to develop a robust and a reliable mechanism to deal with compliance concerns and issues to do with possible non-compliance. And that gets me to the end of my presentation.